Any questions? Yep.
19.
Oh, yes. So we have 3 minus log base 10 of x. That's f of x. And g of x is x squared plus 2. And we want to find f minus g of 10. We want to find f divided by g of 10. And we want to find g of f of 10. So I'm going to simplify this. F minus g of 10 is just f of 10 minus g of 10. F divided by g of 10 is f of 10 over g of 10. And g of f of 10 is just g of f of 10. So I'm basically translating the way we write it into the way that we really use it. Now, it would be helpful to know what f of 10 is. It would be helpful to know what g of 10 is, because we need them for each of the ones below. Three minus log base 10 of 10. And that's where the question comes in, I imagine, right? What the heck is log base 10 of 10? Let me ask the question. I'm going to, what is log base 10 of 10? That's the question, right? I mean, you're literally asking yourself this question in your head. Man, what is log base 10 of 10? Watch me do this really algebraically. Right? What unknown is equal log base 10 of 10? Take this, and you know that logarithmic form is way less well known than exponential form. Rewrite it. 10 to the n power is 10. Now, what does n have to be for that to be true? 1, right? What is log base 10 of 10? 1. Make sense? Whenever you have a log base 10 of some log base whatever and it's in a function, and you're not sure what it is, just ask yourself the question. What is that? 10 to what power is 10? The answer, 1. So this is 3 minus 1, which is 2. The other is going to be 102. Are we okay with that? So we have 2 and 102. So f of 10 minus g of 10 is 2 minus 102. That's negative 100. F of 10 divided by g of 10 is 2 over 102, which is 1/51st, whatever that means. And g of f of 10 is g of 2. Because you know what f of 10 is. F of 10 is just 3 minus 1, which is 2. And what's g of 2? That's going to be 2 squared plus 2. That's going to be 6.
Oh, I get these ones.
Great. Write a passage for this class. Do you get functions? Give it something, it gives you something back. That's all a function is. Input, output. Does that answer the question? Good. You're welcome. That's tricky. That's the first time we ever saw that too. And it was only the second time, like we've seen logs, because we just saw logs in the last section, but now they suddenly throw it at you. You could just as easily, by the way, what if you could do f of 100 easily in your head, because you say 10 to what power is 100? 10 to the 2. Did you say 6? Greg?
No, I said 7.
Second. Oh, okay, good. I was like, no, before class you were claiming you knew how to multiply. I am suspicious. But just to be clear here, if you had this, that would be really, really hard. You'd have to really know your 10s tables. Because I don't know what power you have to raise 10 to get 20. I don't know. It's something. It's more than 1, less than 2. It's somewhere in between. Is it 1.1? I don't know. Like, it should be 10 to the 1 times 10 to the 1 10. Because you add them up, that's 1 and 1/10. That'd be 10 times whatever the square root of 10 is. Or no, that's the 10th root of 10. What number times itself? I don't know. I don't know what it ends up being. I don't want to think about it. A calculator could tell you if you really had to, you know, an itching. But whenever you see these in the problems, it's always going to be to a nice multiple. Even something like that you could do. 10 times itself 3 times. Okay, that would be the 0. F of 10,000 is 0. Okay, anywho, long story short, you'll see those in the future, those log 10 of whatevers, log 5 of whatevers. And they'll almost always give you an input that lines up just right. Other questions? Ooh, we're getting one rock solid with this, aren't we? That's good because we have a quiz next Wednesday.
Oh, that was such a perfect root.
We're about to do the fastest lesson in the history of the math career. Yeah, it's gonna be really fast. This is section 28. Technically, we're only covering half of what the lesson covers, so I'm cheating when I'm saying it's the shortest ever, because the other half of the lesson is crap. So we're just not going to worry about it. But 28 deals with factorial notation. Sounds fancy, doesn't it? Factorial. You see the word factor in factorial, and that should remind you of multiplication, which will help whenever you think of a factorial. If I take a number and put an exclamation point after it, that means factorial. Have you guys seen this
I
before?
remember this.
Some of you may have, some of you may haven't. If you put,
Text talk.
say what?
She goes, it's text talk.
Yeah, I mean, it's like you're like really excited about the number. No. When you have the exclamation point at the end, you just take n times n minus 1 times n minus 2 times until you get down to times 2 times 1. That's all it is. So you basically multiply all of the positive integers less than that number together. So 3 factorial, and you read it as 3 factorial, not 3, right? You read 3 factorial. That's 3 times 2 times 1, or 6. Oh, right? That's all. 4 factorial is just 4 times 3 times 2 times 1, which is 24.
Why do they look like
Well, just imagine a hypothetical situation. Imagine you and 3 other family members who are going to be in a picture. And the picture was the 4 of you standing shoulder to shoulder. And you wanted to think of all the possible ways that you could take the picture, like how many different combinations of people, right? Now maybe it's not a picture taking, and who cares if we get every combination. Maybe it's something where order really matters, and maybe you're like trying to crack a safe or something like that. That would be maybe a more applicable situation, who knows? Maybe not, maybe you're never going to be cracking a safe, hopefully, but anywho, think, you've got these 4 people, right? Person A, person B, person C, and person D. How many options would you have to put into the first spot, the farthest left spot? You would have 4, right? You could either lead with person A, or lead with person B, or lead with person C, or lead with person D, right? Now, assuming you picked one of those, right? Assuming you picked like B, you led with person B. Now, how many options do you have for the next spot? 3, right? Because you could have, assuming we started with B, you could have like BA something, BC something, BD something, really, something, there's 2 somethings afterwards. So you would have 3 options there. Now, assuming you picked someone for that, like say you picked person D for that, how many options would you have for the next spot? You've already got B and D locked. For the next spot, how many options do you have? 2, either person A or person C. Now, assuming you pick one of these combinations, how many people do you have left for the last one? 1, you're forced. It's B, D, A, C. Once you pick the first 3, you're forced to put the last person in the last spot. Right, woe is them, there's no flexibility there, but this could work for all of, like, I could do the same exercise with A's. I could either go A, B, A, C, A, D. And once I go A, B, I could go A, B, C, or A, B, D. And once, so, in other words, how many possible pictures are there? It's just multiplying these things together. 24 possible combinations. That's why we use that, because if you wanted to write this out without having to do all the multiplication, you could just say 4 factorial. Yeah. Does that answer your question? Good. It better. Now, just a thought for a second. Even as I'm writing this out, this is really like 4 times 3 factorial, in a way, right? Just to think about that. And why I say that is because they'll give you problems like this. And they'll say evaluate without a calculator. So, now think about this. If you tried to do this the old-fashioned way without a calculator, 9 times 8, 72, times 7, what's 72 times 7? I have no idea. Times 6, times 5, times 4. That's going to get huge really quick. Factorials get huge really quick. But if you think about it, I'll do it the dummy way first. That's what's on top, right? And what's on bottom is 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1. Now why did I say that's the dummy way? Because you can start to notice the pattern really, really quickly. Whatever the biggest factorial is on bottom or on top, I mean, take the biggest factorial, find the next biggest factorial on the other side of the fraction bar and say, wait a second, 5, 4, 3, 2, 1 is going to cancel 5, 4, 3, 2, 1, right? And then all you have to do is cancel the 3, the 2, and the 1. Well, 3 times 2 is 6, so that'll cancel with the 6. And you're left with 9 times 8 times 7. That's good enough. We don't have to multiply those together. That would take that's a waste of time. We have better things to do with our life than multiply 9 times 8 times 7. 504, if you wanted to know, if you cared. Now let's look. Now let's think, because the dummy way of doing it, or where did I use the dummy way? Okay, sure. The dumb way of doing it will not be horrible in that situation, but in this situation, I would argue horrible might be a word to describe it. You have 14 factorial over 6 factorial, 11 factorial. Oh geez, right? Now, if you wanted to, you could write 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6. That's going to take a heck of a lot of time, and that's just a waste of time. Because find the biggest factorial, 14. Find the next biggest factorial on the other side of the fraction bar, 11. And rewrite this as 14 times 13 times 12 times 11 factorial. Right? And then on bottom, you got your 11 factorial, and those go bye-bye. And then all you have to worry about is the 6's. Well, that one I might actually have to write out. 6 times 5 times 4 times 3 times 2. I'll write the times 1, but think about it for a second. Times 1 does nothing. Okay, so 1 factorial is really uninteresting, and 2 factorial is similarly uninteresting. Yeah. By the way, this is for definitional purposes. You don't have to like that, but that's just the way that it is. This is the way that we define it. That way you can divide by 0 factorial, because in certain cases you might want to. I'll just leave it at that. You don't have to like it, that's just the way it is. Ew, I know. It's like, you can almost think of it as, this is a multiplication property, Do you agree factorials are a multiplication property? It's almost the same idea as that, almost. But not quite. But, yeah, that's just how we do it, that's how we do it. That way you can divide by 0 factorial. So if anyone says can't divide by 0, be like, false. Right, just did it. Okay. I've never thought of that before, that's kind of cute. Okay, let's start canceling away. So the 6 and 2 makes 12. I can cancel a 2 here and there, but then I'm done. 7 doesn't go into anything below, nor there's 13. So on top we've got 7 times 13, and on bottom we've got, well, that. If you wanted to write that out, you could. If you did the whole thing. This is good, by the way. Somebody was looking in the window. Might be our imaginary speaker, maybe.
It's construction worker.
Oh. Maybe not. Okay, we good on this? I mean, once you get the idea, executing it is really not that hard. Say what?
So I'm just like, I don't get it.
And all you gotta know is, why do we use an exclamation point for that? I don't know. I mean, we just do.
Someone's just
People
mad.
like yelling.
Yeah.
He's just like, 4!
Oh, this is great. This is good. This is a big one. The unit circle. Rarely do we use the word the, right? Rarely do we use the word the in math, so this is a big deal. The unit circle. This is, well, it's obviously a circle. I'm not going to rewrite myself. It's a circle of radius 1 that has a center at the origin. That is the unit circle. Centered at 0, 0, radius 1. So it comes out here to what? Over 1, up 0, over 0, up 1, left 1, up 0, and over 0, down 1. This is the unit circle, radius 1. There it is. That's the unit circle soundtrack. If you're curious. Okay. Yes, we have fun in here. Good. Okay. Now let me pick a random point on the unit circle. Okay, I'm going to pick a random point, right? This is some xy. Now, from this point, you'll see where this comes into play here. If I connect out here, that would be a radius, right? He would have a length of 1. Why? Because this is the unit circle. And the unit circle has a radius of 1. Now, if this point is xy, that means he's over x units, right? And he's up y units, which means if I made a triangle and I dropped down, I would have a height of y. And if I looked over, across, I would have a width of x. Yes? Okay. I can always look at my angle in here and evaluate sine, cosine, and tangent. What's the sine of our angle? The sine of our angle would be y over 1, which is just y. What's the cosine of our angle? X over 1, which is just x. And what's the tangent of our angle? Y over x, which, by the way, is also, use substitution, sine over cosine. Ah, whoa, right? Whoa, dun dun dun. If you don't believe me, I mean, that looks almost amazing. Tangent is sine over cosine. Think what sine over cosine is for a second. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. When you divide fractions, you flip and multiply. Hypotenuses cancel, and you get tangent. Every time, right? So that's a true statement always. Interesting, but wait a second. Hold on, wait, let's slow down for a second, because I picked a random point on my unit circle. And my random point on my unit circle is in the form xy. This guy here is a random's the wrong word. I don't want to use the word random. Because random actually, the way that we think of the word random is not how random is. Because random things are actually predictable because they're random. And random things have certain, like, why do I say random things are predictable? It's predictable that the coin comes up heads and tails 50% of the time. Well, it's random, yes. It's predictable because it's random. Because random things act certain ways. I'm not going to use the word random. I'm going to use the word arbitrary. Is this a vocab word? No. What was? You just like the word? Yeah. Or just pick the point. Not even at random. I just did it completely arbitrarily. This is an arbitrary point on the unit circle. Like, what's your reason for doing that? Completely arbitrary. Completely arbitrary. Why did you wear a whatever today? Completely arbitrary. I had no basis for my decision whatsoever, right? So that, yeah, exactly, right? I didn't pick any special. I just picked any point. No basis for my decision whatsoever. But the neat thing about it is, look at this. What is x? X is cosine. What is y? Y is sine. It's because we're on the unit circle, but any arbitrary point on the unit circle is in the form cosine theta comma sine theta. Whoa, okay, now, this is all because of the unit circle, but that's a big box. Any arbitrary point on the unit circle is in the form cosine comma sine.
It kind of is.
Say what?
So my box is opposite.
Now, think about what we just learned yesterday. We learned that when you go quadrant by quadrant by quadrant, all of them are positive in the first quadrant. Only sine is positive. Whoops. Only tangent and only cosine is positive. Did you guys come up with a better acronym?